Hello, my name is Hila, and I'll be presenting the work Optimizing Relevance Maps of Vision Transformers Improves Robustness, which is a collaboration with Idan Schwartz and Leo Wolf from Tel Aviv University. First, let's describe the problem the paper tries to deal with. It is a known fact that vision models tend to rely on spurious cues to make their predictions. In this work, we examine the spurious cues used by vision transformers and find that they suffer from two main issues. The first is over-reliance on the image background, and the second is a sparse consideration of the foreground pixels. The figure here represents examples of both cases. For example, the image here is classified by the model as a chestnut with a confidence of 100%, but the saliency map shows that the model used only the background to make its prediction. This can lead to lack of robustness to distribution shifts and poor generalization. We ask ourselves, can we correct the model's logic? The intuition behind our method is to directly manipulate the relevance maps to solve both issues that we saw before, i.e., demand less relevance on the background and more relevance on the entire foreground, as can be seen in the examples here. For example, originally the model predicted a snowplow based solely on the snow in the background, but after applying our method, the model still predicts a snowplow, but based on the right reasons. Now, let's describe the method. We propose to manipulate the explainability maps of the model directly to ensure that the model avoids using spurious correlations in the background and in the foreground of the image. Our main loss is comprised of two loss functions, L background and L foreground. L background prevents the model from over-interpreting the background by demanding that the relevance on the background is close to zero. L foreground encourages the model to use as much as the foreground as possible by encouraging the relevance on the foreground to be close to 1. Unlike other methods, our method employs the losses during a short fine-tuning process on models that were already pre-trained on ImageNet. We add a classification loss, L classification, to ensure that the accuracy of the models does not decrease due to the fine-tuning process. The formulation of our classification loss is as follows, and it encourages the model to have high confidence on its predictions. Thus, our final loss term is formulated as follows, as a combination of the relevance and the classification loss. We note that in order to apply loss terms on the relevance of the foreground and the background, our method requires segmentation maps to distinguish between the background and the foreground of the input image. We use either human annotated maps or maps produced by Dino without human supervision. Both cases result in a similar improvement to robustness. Our method only uses 3 examples from half the ImageNet classes during the fine-tuning process, meaning an overall of only 1,500 training samples. Our tests employ 3 different types of vision transformers, vanilla VIT, DATE, and VIT with improved augmentations and regularization. We measure the increase in robustness to distribution shifts, i.e., the increase in accuracy for datasets with shifted distributions. We use adversarial, real-world, and synthetic datasets. In these tables, the results demonstrate that our method increases the accuracy significantly on shifted datasets across all the tested datasets that are not from the ImageNet distribution, i.e., not ImageNet Val and not ImageNet V2. For example, the accuracy on the ImageNet A dataset is increased by 5.8% on average across all the architectures with human annotations, and by 6.1% on average with Dino annotations. Next, we present some qualitative results. As you can see, the different models are able to correct the wrong predictions after applying our method. For example, the model here predicts that this school bus is a snowplow due to the presence of the snow in the background. An additional example is this model that classifies the teddy bear as a ping pong ball due to a sparse consideration of only its paw. In both cases, our method is able to correct the wrong predictions by allowing the model to focus on the correct parts of the image. More experiments such as KNN experiments, comparison of training and non-training classes, and a comparison to self-supervised vision transformers can be found in our appendices. Thank you very much for your attention. Please check out our code and paper.